Welcome back to the next installment of Solving Systems of Linear Equations. Just kidding. So, in this one, we are talking about how to solve by graphing or solving with substitution. Okay. So by graphing, remember in general, when we're looking to solve, we are looking for an intersection or where the coordinate is that makes both equations true. We're going to do that both algebraically and with graphing. In our first example here, I actually want you to try it to start. I want you to graph both equations and identify the intersection. Pause and complete. All right, for this one, we're going to take it to a slightly higher level. And this one we have to solve before I can actually graph because I need slope-intercept form to be able to graph these. So I'm going to start with the first one here. I'm going to use that one in blue. Okay, so I have x minus y equals 3. So to solve this, I want to have the y value by itself for slope-intercept form, and I'm going to add y to both sides to do that. So that way I have y positive and I don't have to deal with negative coefficients. But y plus 3 is not what I'm looking for. So what I'm going to have to do is then subtract 3 from both sides. So y is equal to x minus 3, which means I'm going to start at negative 3 on my y-axis based on my y-intercept. And I have a slope of 1, so up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, and so on repeatedly. And then I'm going to draw straight lines through these points. Okay? Strongly recommend you use a straight edge. This one I'm going to use green here, the second equation. So I have 7x minus y equals negative 3. So again, I'm going to add y to both sides so I don't have to deal with the negative coefficient. I'm going to add 3 to both sides then. So y is equal to 7x plus 3. Well, I'm going to start at a positive 3. But here I can't move up 7. So instead of plus 7, I'm going to go negative 7. But if I go negative 7, then I'm going to go negative 1 as well, which brings me down here to my intersecting point. Now I'm going to use red. Let's look at that intersection. We go left 1 and down 4, and our solution is negative 1 for x, negative 4 for y. All right, let's make this happen with substitution. So the very first step you're going to do is you're going to isolate a variable. It does not matter which one. Could be x, could be y. You may already have a variable isolated, but the first thing we need to do is we need a variable by itself. Secondly, once you have a variable alone, you are going to substitute. I know, shock, right? So what that means is we're going to replace the isolated variable in the other equation. Okay, so you should have two equations, so we're going to substitute or replace the isolated variable in the other equation. Finally, we are going to solve, and then we'll repeat this, okay? So once we solve, we'll have another isolated variable, and then we'll repeat as much as necessary until both x and y are identified. Okay. In our first example, I already have an isolated variable. Actually, I have two isolated variables. Y is by itself in both equations. So what I'm going to do is I'm going to take something that y is equal to, in this case x minus 3, and I'm going to place it back in for y. I'm going to put a place for my solution up here. So always use parentheses, overuse parentheses if you need to, when you are substituting, because sometimes you're going to need to distribute or multiply, and it's really important that parentheses are there so you don't accidentally do the wrong operation or forget your distribution, okay? So I replaced y with x minus 3. Now, I got this question in class. Can I replace 4x minus 9 for the second one, like so? And the answer is absolutely. I'm just purely taking the second one because I feel like it, but it works either direction because both of those y values are isolated, okay? So what I'm going to do here is I'm going to solve. I'm going to draw my line. I'm going to start subtracting my x from both sides. Now, I could move my constants first. My goal here is simply to isolate x, and that means I first have to group my variables together. So I have 3x minus 9 over here, negative 3 on this side. And then I'm going to add 9 to both sides. And I have 3x plus 6. Sorry, equals 6. And my final step, I'm going to divide by 3. So x is equal to 2. Now I'm going to repeat, right? So I isolated a variable, or had a variable isolated. I plugged it in for the in the other equation. And now I'm going to cycle back now that I've solved. And I am going to replace x in one or both equations with 2. So I'm going to do this both times, but you only need to write down one. I'm substituting again. And I'm using parentheses, you'll notice, because in this case I have to multiply, okay? Y equals 8 minus 9, y equals 2 minus 3, and in both cases this means that y is equal to negative 1. And it's good to check with both because that helps me know that I did this correctly, because it should work for both equations the same way. This one's going to be a little easier for us because y is already solved. So I'm going to have my solution over here on the side. Y is equal to negative 5. I already know that. It's going to be equal to negative 5 no matter where we are on that line. So I'm going to take negative 5 and plug it in for y, right? Let's do that with yellow. So I have 5x plus 4 times negative 5. Again, really important to use those parentheses when I'm substituting. And now I will simplify and solve. So 4 times negative 5 is negative 20. I guess I don't even need that plus. I can just do 5x minus 20 equals negative 20. And now to solve, I'll do inverse operations. I'll add 20 to both sides. 5x equals 0. But remember, 0 is a solution. So I'm going to divide by 5, and x equals 0. So my whole solution overall is 0, negative 5. And I don't have to necessarily plug this into anything else because we see clearly that y is already solved. For this last example, before you try some on your own, we do need to solve one or both of these to isolate a variable. So I'm going to isolate a variable in this one, and I'm going to isolate x. You can isolate y in either of them or x in either of them, but this is going to be the easiest option for me. Let's actually just solve it right up there. So I'm going to add y to both sides, and x is equal to y plus 13. So I'm going to use this. Let's use red. I'm going to plug it in for y up here. Or sorry, I apologize, that is not correct. I'm going to plug it in for x because it's isolating x. So I have 4. Parentheses are 100% crucial here because I do have to distribute in this case. 2y equals 10. So 4 is being multiplied by everything that x represents, which in this case is y plus 13. So 4 times y is 4y. 4 times 13 is 52. If you aren't sure, or just for the record, I know that because of cards. A deck of cards has 13 per suit, and there are 4 suits, so 4 times 13 is 52 because that's how many decks or how many cards are in a deck. So I have 4y and 2y, which is 6y plus 52. Pulling in all of those skills from solving equations we did in the beginning of the year. I'm going to use my inverse operations now to subtract from both sides. I got 6y is equal to negative 42. And our final step of dividing by 6 means that y is equal to negative 7. But I still need to solve for x. So what I'm going to do here is I am going to substitute negative 7 in for one or both of these. I'm going to use the second one here, but it should work for both. If it doesn't, then we did something wrong. Okay, so we have x plus 7 equals 13, and that means that our answer is x equals 6, positive 6 in this case. So 4 times 6 is 24. 2 times negative 7 is negative 14. 24 minus 14 equals 10, so it works for that as well, meaning this is a good solution here. I would like you to please try this one on your own paper and then continue the video. Go ahead and try this one as well, but you can always come back to this one because this one can be solved either by substitution or by elimination, which you will learn more about in the next video. Have fun.